one presentation less compared to the program. Nicolas Picot couldn't make it. He's still in Toulouse. So 6 presentation totals. We're gonna have 5 presentations this session, and then little coffee break, and then one last presentation. And then we're gonna have at the end the discussion based on the sitting questions that we prepared for the session. So up to David is gonna talk about fully focused SAR in 2 different estuary regions.
Okay, thank you. Good afternoon, everybody. So yes, we're back to fully focused SAR processing. And as Francesco said, we're looking at the potential for using fully focused SAR as part of a coastal monitoring system in 2 different environments. The Severn Estuary in the UK, in the southwest UK between England and Wales, which is a highly dynamic, strongly tidal environment where there's a large river outflowing into a big estuary where there's a big tidal range and strong tidal currents. And then also in the south of France, in the lower Rhone Delta and Camargue, where in contrast, it's a low-lying flat river delta and wetland environment, but susceptible to inundation from precipitation up in the watershed coming down the river and also from rising water levels. It's another project funded by ESA through the EO for Society Open Call. So the kind of basis of the project, the overview, is there's 2 main parts to it. There's applying the fully focused SAR processor by colleagues in DTU space in Copenhagen in these 2 areas to validate that against in situ data and look at its ability to map key features in sea level whilst also optimizing, looking at the best way to process the fully focused SAR data out of the various options that are available. And then also alongside that to install 4 innovative micro gauges by a French company called Vortex.io to provide in situ validation, and then run some drone campaigns to make the connection between where those in situ gauges are situated to the satellite tracks. And then in parallel to that, we're talking to users, see what their key needs are, and to see if fully focused SAR data can add a useful addition to their monitoring set. Projects was initially 12 months, we've extended it to 15 months, but so it's a short time project. So the Vortex gauges, they're really portable. They're in 10 centimeter square boxes. They only weigh, they're less than a kilogram, and you can fix them with strong magnets to any metal structure. So we've installed in Severn Estuary, we've installed one underneath a road bridge in Newport in Wales, over the River Usk entrance to the Severn, and then we're also on a pier, Weston-super-Mare, on the other side of the Severn Estuary. So those 2 locations there. The LiDAR for making the water level measurement, and also a camera from which they can take videos and estimate the water velocity. You can get data in real time. You can manage them remotely, so they're connected just by mobile phone G4, G3, G4, so they can be managed remotely. They have solar panels for power, so they're completely autonomous. And so you can see, since we installed the ones in Newport and Weston-super-Mare in September, just an example of the output. And you can see that the tidal range is over 10 meters on occasions. And the second one is Weston-super-Mare, and you can see that dries out at low tide, so that's why you get the flat bottom terrain. And then the ones in the Rhone Estuary, near the entrance of the Rhone Delta, obviously very little tidal signal inside the Mediterranean, so they're mostly dominated by river flow, I think. They were deployed in July. The plan is to keep them deployed until June this year when the project finishes. I guess if they're found to be useful, then we'll see if we can find a way to keep them installed. And as I say, the idea is those gauges are not directly under the satellite underpasses. So the idea is to fly a drone here with a LiDAR on it from the location of the vortex gauges to the exact position of the satellite overpass, and then run up and down the satellite track. So here, and then the Western-super-Mare one's here, so we'll have to go out from the pier and onto the track, so we can do a direct link of water level from one to the other. The drone can be deployed from boat or from riverbanks, depending on the respective locations. We're planning to deploy them by boat, and we're hoping to be able to do that in the next few months this year. Moving to fully focused SAR processing, it's really the focus of this presentation. So this is carried out by DTU Space, by firstly Heidi Randall and then Karin Nielsen. So they've installed the SMAP processor in DTU and implemented it, and then they're applying it to Sentinel-3A and 3-beta over the two locations. And the plan is that from early processing to identify the optimum processing choices, then generate time series of data, the selected tracks as well as long track data, validate that against in situ data and models, and then once we have those validated data sets, look at how well fully focused SAR process data can resolve fine scale features in these two environments. So in the Severn Estuary, we'll be looking at the small scale physical signals, surface gradients, currents, rough signatures where there's strong tides, which will create asymmetry and gradients over quite small spatial scales. And then over the Rhone Delta, different situation where there'll be lots of different low-lying channels near the footprint. So we'll be looking at how well the fully focused SAR data can distinguish between them. So over the Severn Estuary, we're focusing initially on this track 265, which flies very close to where we've installed the gauge at Newport. So that's been downloaded from Copernicus and processed using SMAP. And first of all, we see the ground tracks of a number of passes over the Newport estuary. The gauge is actually on this bridge here. There's also a longer standing tide gauge on the end of the docks there. And then this is the result from initial processing using the OCOG retracker option. And what we saw was we could see this kind of consistent change in sea level, but very large range, as you see, from over 15 meters. And the first thought was maybe that it was looking at the bathymetry at low tide, but in fact, with a closer look, we could see that it was snagging from off nadir reflections. So as the surface dries out at low tide, it leaves pools of water and it's picking up reflections from off nadir. So here you can see from the 20 hertz SAR altimeter product, you can see that's how the ESA product's picking up these off nadir reflections at the top and also lower down. And then using so this is from the OCOG retracker. First at the top, it's actually following erroneously the 20 hertz data set, but lower down the track, it's actually keeping to the sea surface properly. So it's picking up the water level that's not available from the standard processing. But then DTU, so Karina decided to look at the 10-peak retracker. That's an option, the PTR 10-peak retracker. So you get that just from one pass. I don't know, it must be more than one pass, but you can see that you get a whole range of options, but one of those gives you the true water level along the track. So it's possible from that to actually pick out the true water level, which we needed to use a 10-peak retracker to do. And you can see how either the OCOG retracker or the 20 hertz product just snags to these reflections away from the nadir surface. So this is on a track on the southern end of this track to the southern estuary, Severn Estuary. So having identified the 10-peak retracker as the best option, DTU processed a number of passes from that track and tried to validate against a longer standing tide gauge at Newport on the docks and at Hinkley Point near the power station. And this is the outcome of that validation. So what you can see on these graphs, so the grey in the background is the tide gauge data. The black line is the tide gauge data interpolated to the time of the satellite passes. There are some red points that are flagged on that. Then the purple line is the Sentinel 3B fully focused, so the result from the fully focused SAR processing using the 10P retracker, and then the green line is from the OCOG retracker. And then obviously the left panel's from Newport, the right panel's from Hinkley Point. And on the bottom you can see the residuals from the fully focused SAR processing in blue and OCOG processing in red. So we get an improvement from OCOG from an RMSE of 3 meters down to 1.2 meters. So as I was saying yesterday, there's still a lot of variability, and we need to understand where that's coming from, if it can be improved with retracking, or if it's just variability from the passes not being exactly co-located with the tide gauge. So that's some further work to do on that. And then they're just moving on now to looking at passes over the Rhone Delta. And as it says there, so we're now looking at a low-lying river delta with wetlands. If we're looking at 20 hertz, we only get one estimate as the pass goes across the river. But the problem is, of course, is that you can see the cross-track footprint here passes, in this case, at least 2 areas of water that will give a reflection. So that these number of surfaces within the altimeter footprint make it difficult to identify the right reflecting surface in the processing. So although in principle we can increase the resolution to 50 centimeters, along track we've got this problem across track. And in it, as I say, they're just looking at it in the last month or so. So we found that actually the approach that was found to work best in the 7 isn't working as well for the Rhone Delta, because we're getting a lot of scatter and not finding it easy to pick out the nadir reflections. So there's still some work to do on that. So final outputs of the product. So I'll say we're at the project, we'll continue till June this year. We will be generating fully focused SAR process data sets for the 7 estuary and the Rhone Delta. So there'll be a long track data for the full mission for Sentinel-3A and B, and then time series at some selected locations. We'll have the in situ time series data from the 4 Vortex microstations, and we'll also have the drone campaign data, which will be connecting the sea levels from the microstations to the along track data. If you want to access those data sets, they will become available at this location, at this URL. They're not yet, the site's just being developed, so there's some initial data there, but the SAR process data, the fully focused SAR data is not there yet. Then there'll be, alongside that, there'll be a report with the product validation and evaluation. So we'll have the results of a full validation against in situ and model data at the 2 locations, and then an evaluation of the ability of these data sets to identify and characterize small-scale physical signals in highly tidal regions, any asymmetry and gradients across estuaries due to tides, and hopefully develop an understanding of interaction of tides and river discharge. And then from our discussions with the users, we'll be, as we always do, generating a roadmap that identifies key requirements from user groups and recommendations based on that for how fully focused SAR data could be used in coastal monitoring systems, together with these micro gauges, which are, as I say, very easily deployable and can be moved easily from one site to the other. And I think I've just got some outlook and recommendations. So next steps in the project will be trying to further optimize the processing options for the 7 and for their own, and generating these along track time series data and evaluating the capability to map small scale signals. And then some recommendations potentially for the future. So in terms of user interest from the UK, there's as Dougal will be talking about a little bit later on, there's the swap validation campaign being planned later in the year. So it might be that we can make some contribution to that. Talking to colleagues in the UK Hydrographic Office, they've got plans to update their vertical offshore reference frame. So we think that some of these data could be very helpful in that, in bringing the data right up to the coastline. And we've also heard from some users that they're very interested in the ability to potentially map areas that are difficult to access in the intertidal region. So where there's wet, muddy bottoms to the seafloor, it's very difficult to access to make measurements physically. So they're interested to see if fully focused SAR could do that. And then in France, they're interested in the coastal and flooding and erosion in that area, how in the river discharges, and then how sea level rise may result in salinisation of the water further inland. And that's everything. Thank you.
Thanks a lot, David. Perfect timing. We have time for a couple of questions. So if anybody has questions, please move on towards the microphone.
Okay, thank you for your presentation, which was very nice. If I recall correctly, you showed that the fully focused SAR was able to distinguish when the altimeter was, when the standard L2 processing was looking off the site from the nadir point.
Yeah.
Do you think there is a possibility of knowing where the L2 processing is not looking at the right direction without using the fully focused SAR? Because it's expensive, so it would be very nice to have some training data or whatever, and just have a proxy for knowing if the processing is right or not.
Yeah, I guess you'd have to try and generate some kind of expected profile for that track, and then you'd identify when they were where there were not nadir reflections. Because you get a big jump in range, it's usually fairly evident if you get a sudden step in range that you're not looking at the nadir track anymore.
Yeah, David. Probably this is a follow-on a similar question, is because you were showing that depending on what river you have, and now here also in one of the conclusions, is that you would need to do something different. Yeah. What is that in your view, or what the possibilities does there, or what limitations does it give you to build these kind of things operationally, to get water levels or even flow or whatever downhill you would get from that, from fully focused or any altimeter product for inland waters?
Yeah. So I think you'd probably have to build a processor that characterized different regions and environments, and have some kind of adaptive process that picked the retracker that suited that environment. And whether that was some kind of intelligent system, or whether you just, like Philippa Berry had for land, whether you just characterized it and applied a different processor to different types of regions. We found in the hydrocoastal and land water studies, we certainly found that some retrackers work better in different types of regions to others. So for some glacial areas and ice-covered lakes, one of the retrackers work much better than others, and then for steeply sided valleys. So I think it's the same for coastal environments. If you've got low-lying flat estuaries, then one type of processing will work better. If you've got steep, complicated topography with lots of little islands, then another one. So I think in the end, we're going to have to work out a way to kind of stitch together output from different retrackers.
Yeah, that would suggest that this is still feasible for a satellite like Sentinel-6, which only has a 10-year orbit and only has a relatively limited amount of couple of thousands of targets.
Yeah.
If you go to the 27-day orbit for Sentinel-3 and then you have 2 satellites, it becomes an astronomical problem to do it exactly right for every single crossing. So, yeah, it puts these things in perspective.
Yeah,
that's for sure.
But I think the thing is, there's no one retracker which is going to work best in all environments. It's just doesn't exist.
Thank you, David. Okay. More questions? So the next talk will be given by Carol Bello about the Albatross project.
Did you want the PDF?
That's it.
Sure.
Thank you. Not working.
Why don't you have this bar list?
Huh? Ah.
Just that.
Okay. Okay.
We can see the menu.
Logic. Thank you. So good afternoon, everyone. My name is Carol Bello, and I'm the new project manager of the Albatross project. I'm going to present a review of the work performed on the Albatross project, but first of all, I would like to acknowledge all the co-authors of this work from Novelties, but also from the DTU Space, the University College of London, the Norwegian Polar Institute, the Lagos, and of course people of the ESA-ESRIN for the funding. So Albatross is a 2-year project funded by ESA in the frame of the Polar Science Cluster and the EO4 Society program. You can find more details, technical documents, and products on the website albatross.novelties.fr. So now to get a bit of context, all oceans are connected in one global ocean where the Southern Ocean plays a major role. Thus, this is very important to have a good knowledge on bathymetry and ocean tides in the polar regions to understand a coupled dynamical response of the ocean, sea ice, and ice shelf system. For example, if you take a look at these 2 maps, on the left you have the vector differences for the M2 component with a bathymetry that does not take into account accurate information about ice shelf regions in Antarctica. And on the right you have the same thing, but with a different bathymetry that does take into account accurate information about ice shelf regions in Antarctica. And you can see that on the right you have a strong improvement of the vector difference, and not only around Antarctica but in the whole globe. So that shows clearly the importance of accurate bathymetry and also the fact that the Southern Ocean plays a major role. However, the knowledge on ocean tides in the Southern Ocean is still limited by several factors, such as in situ and satellite observation, availability and accuracy, but also bathymetry quality, coastline ground line location, and so on. And the Albatros project aims to improve knowledge on both the bathymetry around Antarctica and also the ocean tides in the Southern Ocean by the implementation of a high-resolution hydrodynamic model. To be more precise, the objectives of the Albatros project are to use satellite observation to improve the bathymetry, the grounding line, and the coastline information, to explore linkage between sea ice roughness, bathymetry gradients, and tides, to retrieve tidal estimates from cryosat-2 data, to implement a new high-resolution tidal model with data assimilation, and finally to share information and knowledge with other part of science initiatives and projects, and this is why I'm here today. If we take a look at the tidal estimates from cryosat-2 altimetry data, this was a work performed by the DTU Space and Ole Andersen. Ole used a specific retracking with the ESA G-pod service and a combination of cryosat-2 dataset, but also of different datasets from different satellites mission. He averaged the information to obtain a valuable new altimetry dataset, as we can see on the table on the right. If we compare it, for example, with the FES 2014. And this new valuable new altimetry datasets will be useful to explore tides in the Southern Ocean, but also to validate and assimilate models. Speaking of models, the high-resolution regional tidal modeling is performed by Noveltis. The tidal modeling strategy is based on the TUGO-M hydrodynamic model, which is developed by Florent Liard at the Lagos. It uses the same approach as for the FES 2014 and the FES 2022 global models, which mean a high-resolution, unstructured mesh grid and a careful definition of the model extents. For example, the boundaries do not cross any bathymetry gradients or tidal energy flux features. And also, the model has to cover the Kerguelen Islands. So first, we perform a regional and local tuning of the model parameters, which are bathymetry, bottom friction, the friction under the ice, and the rev drag, to obtain the best tidal simulation. And then we use altimetry and tide gauge data assimilation to constrain the solution and to validate tidal simulations. So, for example, if we take a look at the resolution of the FES 2014 global mesh in the Southern Ocean on the left, and if we compare it to the resolution of the Albatros regional mesh on the right, we have a number of elements that have been multiplied by 7. In order to have an accurate and complete bathymetry information is crucial for tidal modeling. And the DTU Space performed a work concerning the improvement of bathymetry in the deep ocean using the fact that bathymetry and gravity are correlated on a limited spectral bandwidth. And that if we find the right scaling factor S, we can obtain a predicted bathymetry by using gravity inversion. So this is what you can see on the bottom right of the slide. The map on the left is showing the DTU-21 gravity field, and the map on the right is showing the predicted bathymetry that is obtained with this gravity inversion. And we can see that there is a consistent pattern showing the fact that there is a correlation between gravity and bathymetry on this limited spectral bandwidth. Then this predicted bathymetry that was obtained is compared to the prior bathymetry dataset, which is a combination of the bend machine and R-topo bathymetries to cover the whole area of interest. And if we look at the results, we can see that there is a local improvement concerning the standard deviation, but the direct validation was limited due to a lack of independent data. However, the high-sensitive hydrodynamic tidal model can be used as a proxy to assess this new bathymetry model. And if we look at bar graph, on the left you have the vector differences on M2 tides, and on the right for K1 tides. And if you look at the DTU Albatros bathymetry, In orange, you can see that it is already at the level of the FES 2014, even if it is not assimilated yet. So now that we have an accurate bathymetry in the deep ocean, it is also important to have a consistent coastline grounding line, but also ice shelves bathymetry to have a high sensitive tidal model. And so this was a work performed by the Norwegian Polar Institute and Guillermo Holt. Geir used existing dataset from different missions, for example, Cryosat-2, but also ICESat-2 and Sentinel-2. And he combined them to update the mask for grounding line and coastline, but also to update the ice shelf bathymetry and ice draft. And now if we compare the mesh grid based on this new Albatros combined grounding line and coastline on the right with mesh grid based on the GS-HHS coastline on the left, we can see that there is an improvement on the right with a more accurate mesh grid and less artifacts, for example, in this region. And now if we look at the tidal model of the Albatros project, but on the left, the vector differences for the M2 component with the GS-HHS coastline and the prior reference bathymetry, and on the right with the new coastline and the new Albatros bathymetry, we can see that in the VDRC there is an important improvement and in fact a reduction by a factor 3 of the errors. So this is very encouraging. And I already said that, but we can see that the impact of bathymetry choice is very important for the tidal simulation, and that even if our Albatros model is not fine-tuned yet, it is already at the level of the FES 2014 assimilated model, for example. And now there was also work concerning the sea ice surface roughness and the bathymetry gradient location. This is a work performed by the University College of London and Michel Tsamados. Basically, it consists in exploring the linkage between sea ice roughness bathymetry and ocean tides. And to use sea ice properties as a surface simulator to locate a non-bathymetry gradient. And for example, in reduced ice thickness or roughness regions, it would be synonymous of vertical excursion and steep bathymetry. So to do so, the University College of London used a novel technique based on 20 years of NASA MISR data for training. This is still a work under exploration, but to summarize it, we can say that first it consists in identifying regions of frequent low roughness or thickness sea ice, and to create this region with bathymetry features and tidal signal, then to produce a regression model of bathymetry as a function of tidal signal and sea ice surface signature, and finally to refine the location of the bathymetry slopes region in poorly sampled regions. So this is a work which is still under exploration, but there is already preliminary encouraging results. And you can find more on the Johnson and al. Scientific publication on the remote sensing for a similar approach, but in the Arctic Ocean. To conclude, we have seen that the Cryosat-2 data are extremely valuable for tidal estimates and bathymetry retrievals. We've also seen that the new Albatros projects bring clear improvement and that the results on tidal simulations are very encouraging for now. But there is a main difficulty, and this is the fact that independent validation is quite limited because of lack of in-situ observation for bathymetry, but also for tides. The last steps of the project are the finalization of the regional tidal atlas by performing the assimilation of the model, and then impact assessment both in the ocean and in ice shelves, which is work that will be performed respectively by the University College of London and the Norwegian Polar Institute. There is also the redaction of a public scientific roadmap with a recommendation for future projects that will be available soon. And finally, the planned outcomes of the Albatross project are the Southern Ocean Composite Bathymetry, an Antarctic grounding line and coastline, a sea ice surface roughness product, and a Southern Ocean high-resolution tidal atlas. And if you are interested in taking part in the pre-release assessment that will be in February and March, you can contact us and we will be very happy to work with you. And that's it. Thank you for your attention.
Any questions?
Yeah, Carol, this was very, very dense with information. I will need to,
Yes.
I will need to read your presentation afterwards. But I just want to do one little plug for GMT, as I'm also a developer of GMT, from which you got the GS-HSS coastline. Could you share your new coastline with Paul Wessel, and so that we can update GS-HSS with this? Because we know that the coastline of Antarctica is pretty bad.
Okay.
So we would love to get your input.
Okay. So the project is not yet finalized, but I think that it is in the planned outcomes to share the grounding line and coastline. So
Okay,
we
good.
can discuss.
I also have a question, out of curiosity. So you're using this structure grid that is refined depending on the coastline, but I assume ice is also has an impact on the propagation of the tide. So I was wondering if refining your unstructured grid also based on the maximal extent of where ice can reach might help improving the model.
Yes, I think so, but I am quite new on the project, so I am I am not able to say. I think that I don't want to say bad things, but I think it would be interesting, but I am not able to say if it has been studied yet on the early times of the project or not.
Okay, thanks a lot. All right, we move on to the next speaker. We are surprisingly in time, but unless there are more questions. Sorry about that. Lofty.
You mentioned that there is a wave drag on the hydrodynamic model. So how do you manage that? Because of very strong uncertainties related to the wind and waves in the Southern Ocean.
I am not the person that has developed the tidal model, so I am not able to answer this question. But my colleagues are here today, so I invite you to join us later so we can discuss that point.
All right, I guess now no more questions, so I can go on and say thanks a lot for being in time. Next speaker is going to be Elodie da Silva, also from Novelties, and is going to present us some results from ESA street art project.
So yes, I'm here to present the street art project. So it's a project led by Novelties and with 3 thematic teams. So one thematic team for hydrology, which is led by Nicolas Picot from CNES and Jean-Christophe Poisson from Vortex.io. One CIS team led by Henriette Scorob from DTU, and one land ice team led by Guillermo Hod from NPI. And you can see below all the partners of the consortium. It's a big consortium of 17 companies. And so just street art stands for Sentinel-3 Topography Mission Assessment through reference techniques. And the main objective of the project is to prepare the ground to ensure an operational provision of fiduciary reference measurements to support the Sentinel-3 land STM mission over inland waters. So it covers rivers, lakes, and estuaries, sea ice, and land ice. It's a 21-month project, which started on July 21 and will finish in April this year. So a detailed view of the objectives of the project. So first, we have the definition and consolidation of methods and protocols for the validation of Sentinel-3 altimetry land products with some fiduciary reference measurements. For that, we have also campaigns where we will deploy and operate some in-situ sensor in order to collect FRM data and to provide FRM data to the Copernicus Sentinel-3 validation team. And finally, the main outcome of the project will be a roadmap that will permit to assess the needs for permanent sensors and campaigns and to prepare some operational scenarios to provide the FRM data to support the Sentinel-3 altimetry land validation. And in parallel of these main objectives, there are two tools that have been developed during the project, ScaleSheet and the FRM Data Hub. I will present them a bit later. So to go towards this roadmap, we have been going through several steps. So the first one was to identify the measurand to focus on, reviewing altimetry measurement uncertainties. So then we have also done a review of all in-situ sensors available, and we have, let's say, ranked them according to their adequation to FRM needs. We have identified some super sites to deploy sensors and deployed these sensors on field. And finally, we are now in the 5-step and 5-6, which are the comparison of the measures acquired during the campaign with Sentinel-3 data and the analysis of uncertainties and the definition of the roadmap. So just to precise that the campaign part has been done only for the hydro team and the sea ice team. So the work is much more advanced for these two teams. Land ice is more small part of the project. So you can see on the screen some illustration of the different campaigns, of the different types of sensors deployed on inland waters and on sea ice. Focus on inland waters. Lots of campaigns have been realized. 18 Vortex.io microstation have been installed on super sites over the Rhine River in France, on the Po River in Italy, Garonne River in France, Tiber River in Italy, on the Seine estuary and on the Canal du Midi in France, and finally more to come in the Dutch part of the Rhine. Some drone campaigns have been performed over the same rivers in order to measure and evaluate the topography of the river, because we will see later on that we need some measurements of the slope of the river in order to calculate FRM. We have also been deployed some pressure sensors where microstation can be installed, because to install a microstation we need, for example, a bridge, and we do not have the bridge. All bridges are not under Sentinel-3 tracks, so we have to find other solutions. So this is an example of pressure sensor. And finally, these images illustrate some tests that have been realized in basin. So it's a test basin in Marseille that's enabled to evaluate the uncertainties of the sensor according to the water rigorosity and the waves conditions. Okay, so now come to the strategy for FRM provisioning. So the Sentinel-3 MPC requirements for FRM are the following: a reliable timeliness inferior to 1 or 2 days, ideally. Georeferenced sensors shall be used for an absolute comparison of water surface elevation. We need long time series in order to detect anomaly, at least 1 year to cover a full hydrological cycle. We need also a variety of configuration in order to compare different configuration relative to Sentinel-3 tracks orientation. And also we need different complexity of sites in order to understand and provide a complete error budget. So the approach that have been adopted during the project is a complementary approach with 2 types of sites: what we call the Calval super sites and what we call the opportunity sites. So the Calval super sites will be sites installed and managed and maintained by the project to ensure the operationality, so not to depend on any third party. These super sites are also fully instrumented because they will serve as a reference, so we need to know very well all the uncertainties on these super sites. And so we will have different kind of measurements to understand also Sentinel-3 measurements, so such as slope, roughness, water depth, surface velocity. And finally, they shall be selected to be representative of different measurement configurations. And so this is for Calval super sites, and we have to complete that by opportunity sites. So the idea is to take advantage of all the existing in-situ sensors from the different countries, because there are already lots of hydrological networks in the different countries, and to increase the number of opportunity sites to provide statistical analysis of Sentinel-3 performance over inland waters. Okay, so for the super site, classification of super sites has been done, and according to the classification of the super site, we will have different process to calculate the FRM. So, well, I will not go into the detail of the different classes of rivers, but the idea is to identify if the river is with a big slope or not, if the measured point is under Sentinel-3 tracks or well, not very close to the Sentinel-3 track. So in case we need to take into account the propagation time or not. Yes, basically that's it. And so, as you can see, our super Calval sites are already covering the different classes of rivers, so that we have today within the project an ensemble of super sites which is quite representative of the different configuration we could find for Sentinel-3 Calval. And then, so standard processing is under development for each complexity level. So in any case, the standard, let's say, steps are the following. So we use the center line of the river. We also have to know what is the river profile. So what is the water evolution. And so we do some measurements with drone for that. We have also to compute the propagation time of the water. And finally, we have to compute the water surface elevation from in-situ data at the actual virtual station position of Sentinel-3 track. So these are some examples of the results already produced, but the objective of today is not to do a presentation of the results, but just to illustrate. So this is for the Garonne River. We can see that we have a difference between what has been measured at the Marmont station and what has been measured on Sentinel-3. The difference is of 10 centimeters. And on the Canal du Midi, which is, let's say, as an ideal case, because the river is very flat, there is no roughness, there is no slope, and the position of the station is almost under the Sentinel-3 track. We have an RMSE of 5 centimeters. Just as we are in the coastal altimetry workshop, a quick focus on Honfleur. So the case of Honfleur, we also installed a micro station just behind, almost behind the Sentinel-3 track on this infrastructure, and this harbor infrastructure. And this is the time series of water surface measured by the Honfleur station. So as we can expect, we have the influence of tides. And so for estuarine regions, the calculation of the FRM will be much more complicated because we need to have a very precise knowledge of what is the impact of the sea on the river. I will not enter into the detail because there is a very good presentation of my colleague Ramiro Ferrari tomorrow dedicated to the development of regional high-resolution hydrodynamics models in estuarine regions, focused on Seine and Elbe estuaries. Okay, so a very quick overview of what is done on CI side. So basically, it's quite the same approach. We have a selection of an evaluation of the different FRM sensors available, classified permanent, semi-permanent, and campaigns sensors. And we have constructed FRM compliancy matrix to rank the different sensors according to their maturity in terms of uncertainties. And two campaigns have been done, one in Baffin Bay campaign in order to get some coincident observation with multiple sensors and to test also new techniques and put it in correlation with proven sensors. And another campaign has been done on Arctica this summer in order to evaluate the difficulty to deploy a drone from an icebreaker and to evaluate also the precise positioning without differential GPS to support the drone observations. One aspect of the project which is very important is the analysis of uncertainty. So for that, we have received support from the NPL, National Physical Laboratory in UK. And so we adopt the metrology approach, which is composed of all these steps. So I will not replace Emma Williams and do a very extensive presentation on metrology, but just a very quick focus. First, we analyze the measurand and what is the difference between the measurand obtained within the in-situ station and the equivalent altimetry measurement. So what are the processes we have to do to transform the in-situ measurement into the equivalent altimetric measurement. And then we have to do this comparison diagram. So this comparison diagram permits to visualize the different validation interfaces. So it highlights the different reference observation and processing steps required to reach a similar measurement for comparison. So we can see here the different steps. And finally, we transform this comparison diagram into an uncertainty tree diagram, which identifies all the uncertainties at each step of the processing. So very quickly, the two tools that have been developed within this project. So the ScalSit tool, which is a tool that permits to identify some super sites over inland waters. So the idea is to put in input the water surface mask, the satellite orbits, and some user parameters. And ScalSit will calculate all the intersection between the water mask and the satellite orbits. And we will get in output the super calval sites, so the intersection between the river and the satellite tracks. This tool has been developed as a QGIS plugin, so it is quite easy to use. And another tool that has been developed is the FRM Data Hub. So the idea of this Data Hub is to centralize all the FRM measurements and to federate the Calval community in order to share all the FRM measurements in a free and accessible manner. With important aspect, all the FRM processing and measurements documented. So for that, we have a defined format. Yes, there is a file name convention also. And so the first step is to integrate all the data from street art campaigns. And the next step will be to integrate any FRM measurements. So for the outlook and recommendations, so the recommendation for hydrology, I focus on hydrology, is the importance to deploy instruments managed and maintained by the project to ensure the operationality of Calval super sites. To take into account the multi-mission aspect in order to determine super sites, to share costs, because if we put a micro station under several missions, it permits to have to share the costs between the different missions. Also, the importance to have super sites which are representative of the different measurement configuration, and of course to deploy as many super sites as possible. Another important thing is also to rely on the existing in-situ networks in order to increase the number of opportunity sites to provide a statistical analysis of Sentinel-3 performance over inland water. And some recommendation for the FRM aspect. So the analysis of uncertainties in this globality is quite complex. A document has been written by NPL and, in collaboration with NPL and with the consortium. This document is a FRM meteorological traceability document, and it appears to be a good template, and it may be used on other projects. So if you are interested in having a view, if you are interested by this document, please contact us, and we will be happy to share it with you. Thanks for your attention. This is a link towards the website and my email address in case you have any additional questions.
All right. Thank you, Elodie, for the presentation and for being in time. There are times for a few questions, or for one or two quick questions. Okay, just one question. When you show the characterization of the different sites depending on their difficulty, I was a bit surprised not to see a parameter like the river width as considered as whether a site is more challenging than another. Is that because it's something that is being completely thrown out and you're doing measurements on sections where the width is big enough, or?
I think it's because it doesn't have a lot of importance. At least on the sites that have been studied, I know that, for example, the Canal du Midi, which is very narrow, it doesn't present a difficulty, the fact that it is narrow, because it depends on, of course, if you have other water surfaces around, it's more difficult. But where we install the station, there is no other water surface around, and so even if it's very narrow, this is not a difficulty. I'm not a altimetry expert, so maybe there is some difficulties when it's very large, because I think that the other parameters will intervene. It's not due to the width, but we'll have maybe more roughness or more other, maybe the topography of the river will be more complex if it's larger, but finally it doesn't seem that it's the width itself that plays an important role.
Thank you.
So the next talk,
Luciana?
I wanted just to ask you, so I didn't understand really, are you thinking to put all this information to consider the crossing of the river with Sentinel-3, Sentinel-6, or everything? Because I have the impression that you have much many points than the crossing of Sentinel-3. It's called Sentinel-3 start?
No, on which... You mean on which one? On
So you had pictures with a lot of station
Yes,
in
this
Europe.
one.
Yeah, yeah.
This one.
So this is
This one represents all the opportunity sites under Sentinel-3 tracks.
so opportunity sites. Definition of opportunity sites are the red circle.
Yeah, all the cross is Sentinel-3 tracks, and the pink points are the position of French network, Vigicru.
Yeah, okay.
And so we have selected only the Vigicru stations that are under Sentinel-3 tracks.
Yeah, because I see, for example, the Rhine, you have Mainz, it's not anymore a French network.
Why there are so many here, for example?
Yeah, yeah, this is the French network, but you go to, you have all the tie gauge that exist, probably.
Yeah.
Okay,
All these gauges already exist within the French network, and if they appear there, because I think that they are well, I didn't display the Sentinel-3B track, but I suppose they are under the Sentinel-3B track.
Yeah,
because
you have. I think that you have all the gauges.
we have only taken into account Sentinel-3A and Sentinel-3B gauges.
Yeah, yeah. And the project goes until the project is finishing
In April.
in April. Okay.
Yeah, it's almost finished. Yeah.
Okay, thank you, Elodie. So the next talk is about the cryotempical solution thematic data product given by Francesco.
I can't read this stuff. Doesn't disappear. Okay. Almost there, eh? Bear with me. Okay, so what I'm going to talk today is about the CryoTempo project, which is an ESA-funded project. And the result I'm going to present has been developed in collaboration with a bunch of colleagues from CLS, IMEDEA, ESA EUMETSAT, and there's a part also with Noveltis now. So what is Cryosat? Cryosat is an ESA project that aims at exploiting cryosat observation from different surfaces. And the idea is that although Cryosat is a mission that has been primarily designed for the cryosphere, is also the first mission that was based on SAR technology, and as has been seen several times already over the course of the last couple of days, SAR altimetry has lots of advantages compared to traditional altimetry in terms of resolution and signal-to-noise ratio. And because of that, those measurements are much better, well suited for the analysis over several different geophysical surfaces. So CryoTempo is a project that focuses on 5 different geophysical surfaces, and there are 15 institutions across Europe involved in the consortium, and the part that I'm in charge of is the coastal ocean part. So the coastal ocean product focuses for the moment on the Mediterranean region, and here's just a picture, an image of the domain, the extension of the domain, with in orange the tracks in LRM and in blue the tracks in SAR, because Cryosat has different mode of acquisition. The product is generated for the whole duration of the Cryosat mission and is updated operationally every month. Just notice that Cryosat mask has been changing over the years, and since December 2015, there's been a big change that brought SAR measurements pretty much all over the Mediterranean basin, with a big patch of SARIN observation over the Aegean Sea that at the moment is not included in the product, but will be included in the future version of the product. The product is, the concept is to have a product that is easy to use also for the non-expert or non-altimeter expert. So it includes just a subset of key variables which are listed there. In terms of geophysical variables, we have sea level anomaly, absolute dynamic topography that are provided in raw and filtered format. We provide now also distance from the coast, and there are, of course, flags designing the instrument mode and whether raw observation should be considered valid or invalid. To access the data, there are two main access points. The first one is the ESA Cryosat server, and the other one is the dedicated CryoTempo web portal. And the web portal is really the easiest way to quickly access and visualize the data. Here is the example of the access page. You have pages like this for all 5 different products. So even if you're not interested in the Mediterranean product and you're interested more in land or sea ice or hydrology products, I recommend you to go to the website. Again, link is here. You can access and visualize the different variables in terms of maps. We have distribution of the data for each month. So those are monthly maps. We have, I don't know if you see it here, but those are maps with missing points. And the other option is also to visualize the time series. And this is just the time series of SLA filtered for the whole basin. So the production cycles, I mean, the CryoTempo, it's a project that sort of produce, rinse, and repeat. So we have like each year, we have 5 steps that we follow. And those are going to be, they've been already performed for a couple of years, and they will be performed for the next 5 years. So each year we provide a new version of the product. And the idea is to define the products, start a test production, reprocess the whole data set, and then start operational generation. And the important thing is that we have within the project, we have a set of experts that are involved on the definition and the evaluation of the products. They provide feedbacks at the end of each cycle. And what we would like to have now is to have users that will start to download the data, use them, and provide feedbacks also depending on what feature they will like, what feature they don't like, and what improvements they think that we should bring to the product. For the moment, the first version of the product is already available. The second version has been produced, and I think is going to be available starting from mid-February. We still are ironing out the last couple of little details, but it's going to be ready soon. And we've already started thinking and producing the new evolution for the third version of the product. So in terms of what the product contains, so the product is a 20-year product, and we brought a bunch of variation compared to the standard products, because the idea is to create a new product with the state-of-the-art corrections, retracking, and options for the processing of coastal and ocean observation. And so here in bold are all the differences compared to the official GOP Cryosat products. And the things that I'm going to focus today especially are the retracker, the ocean tides, and the HFA correction. So in terms of the retracker, all the SAR observation have been retracked using the Samosa Plus retracker that's been developed by Salvatore Di Nardo. And the really good thing about the project is that we were asked by ESA to release an open source Python version of the product. So now we have a GitHub repository where everybody can just go download the Samosa retracker and play with it. We decided, since the idea was to improve as much as possible the coastal product, we decided to apply the HFA correction, which is a correction that removes part of the error that is associated with the significant wave height. So there's a correlation between the error in significant wave height and in altimetry, and the HFA correction corrects for this error. And here is a map, for instance, of the difference in variance between the official product and the CryoTempo product average over boxes of 1 degree, I think. Yes, half a degree. And what we see is that especially in the, I lost my okay. Especially in the low resolution LRM portion of the basin, we have a big reduction in variance, meaning that we have less noise, meaning that the HFA correction works as expected. In terms of the second version of the product, we we added some new features. The main ones are, well, we extended the model to the Black Sea. We included the regional tidal model that was developed in collaboration with Noveltis. And the main thing is that we improved the uncertainty estimation. And the uncertainty estimation, as I talked in a little bit, was something that was really stressed by ESA for this type of products. In terms of regional tide, again, it's provided by Noveltis. It's based on the regional regat-met model, 34 tidal components, and it's based on improved bathymetry and near coastal resolution via unstructured grid. Here I'm showing to the left the Noveltis tide, the regional tide, and to the right the tide that comes from the products. They are both fairly similar. When we take the difference, we see some differences that are on the order of the millimeter scale. One thing that I would like to point out is that for the moment, the tidal product, this regional tidal product seems to be an improvement, but it still has some limitation in terms of the fact that it does not contain the Black Sea basin and does not provide the loading tide. And those are aspects that will be improved with the new version of the product, hopefully. In terms of certainty, as I said, ESA really remarked the importance of having uncertainty estimation coming with our sea level observations. That's because often users require this type of evaluations for their application. Think about, for instance, data simulation. And therefore, we come out with the scheme to refine the estimation of this uncertainty. And here I'm just talking briefly about the estimation of what we call the small wavelength errors. And those are the errors that can be hypothesized as be associated with the individual measurements, and they are mostly due to significant wave height and the distance from the coast. So the way we computed those uncertainties is starting from the hypothesis that consecutive measurements at 20 years roughly observe the same conditions. Therefore, we can take the first difference of 20 years measurements, and we can bin those variations based on significant wave height and distance from the coast. And the standard deviation of each bin, of the difference within each bin, provides an evaluation of the error. And therefore, we build up a two-dimensional sort of lookup table in which the error varies as a distance from the coast and the significant wave height. And what we can see is that regarding significant wave height, the error increases with significant wave height. And regarding with the coast, it strongly is roughly the same for 5 kilometers or far offshore, and increase really quickly within 5 kilometers to the shore. So that's the way we compute it. So the error for each measurement was computed as a function of distance from the coast and observed significant wave height associated with that observation. We also improve and try to limit the bias between our observation in LRM and SAR. So here it's a map with the difference between consecutive points, and we have at the boundary between SAR and LRM observation, we see big jumps that are visible here in orange and blue. What we did before is just we treated LRM and SAR granules as separate. So when we filtered the SLA, we started to have boundary effects at the edge of each granule. This boundary effect completely disappears if we stitch together the granules in LRM and SAR before applying the filter. And if we do that, we have a very nice and continuous SLA series along the track. The product now includes, again, the distance from the coast. I think it's very useful for doing analysis of the data in the reference frame of the distance from the coast. And the variable that we computed is based on the GSSHG database. And this new variable allowed us to refine the masking of the points near the coast. And here I'm just showing the comparison between the previous version of the product, where the flagging was based on what's available in the GOP product. Those are the points, the distance from the coast provided by the new data set. And so we updated the flagging, showing that now we have a much better flagging of valid, invalid, and land points. And based on the new flagging, we decided to remove land points from the data set since we are focusing only on the ocean points. And the flagging works really well also on areas of very complex coastline morphology. Finally, we keep refining the parameters that are used to define the different products. What we have here is a spectral analysis of SAR in blue and LRM in orange, SLA observation from the product. So the blue spectra are based on this segment, orange spectra are based on this segment. What we see here is the end. Here in the dashed line is the cutoff wavelength of the filter that we apply to compute the filter solution. What we see here is that probably these spectra show that the plateau that is expected to occur at LRM observation ends up a bit earlier than the cutoff wavelength that we choose. And therefore, we might have filtering a bit too much. So we've been start testing if a smaller cutoff distance would be better for the product. And this option is being under evaluation by the tags. And speaking of tag evaluation, the product was also compared to in situ observations. And that's a work that's been developed by colleagues at EMEDA. So the first part of the validation is comparison with the tide gauges. There are 16 tide gauges in the western part of the Mediterranean. And the way the comparison was performed, as Jesus already showed yesterday, we just took a radius of 0.3 degree around each tide gauges, and all the observation of each pass of cryosat that went through that area were averaged together and then compared to the nearest in time tide gauge observation from each tide gauge. And this is the time series for the different tide gauges for two separate cryosat passages. And what we can see is that the correlation is relatively good. The root mean square error is not that bad either. And in general, we are doing much better than the official GOP product. And that's part that is not shown here. We also compared against HF radar velocities. The HF radar velocities were pre-processed to remove the adiostrophic portion of the signal and the tidal component of the signal. And the comparison, again, seems to be qualitatively okay. There are still some errors due to the small scale, and further analysis would be required to further refine this type of validation. Finally, as I said, we have started developing the third version of the product. So the main changes would be the inclusion of siren observation to fill that big hole in the GNC that I showed you early. We extend the domain to the Northeast Atlantic, hoping to catch a bit more, larger number of users that would be willing to use the product. And since we're extending the domain in a larger area, we reassess all the altimeter mode biases in SSH. And we keep refining the correction parameterization used to derive those products. So to conclude, cryosat observation remain underutilized. So ESA decided to finance the CryoTempo project, where we use those nice SAR observation over different geophysical variables. The product that we have for coastal ocean shows quite promising results, especially compared to the official product, but there's still lots of room for improvements, especially in the nearshore region. I mean, as I show, we haven't really done anything too much coastal specific in the project, in the product yet, except of using the Samosa Plus retracker, which is by definition a very good coastal retracker. Again, the product is going to be refined each year. There's going to be other 3 versions of the product in the next 3 years that's going to come out. And so what we need now is just you start playing with that product and give us your feedback so that we can keep improving the product and make it as sweeter as possible to your needs. In terms of outlook and recommendation for this session, what I can say is that coming from the CryoTempo experience, the dedicated processing chains are really important for testing a new solution and the state-of-the-art procedure for a generation of coastal regions. But the big problem is that these dedicated product needs to be assessed. And that's one of the big issue at the moment, because for the moment, the idea has been always to do projects that do a round-robin experiment, gathering all the different products that has been generated. The problem is that this product kept being generated, so it's going to be a sort of an infinite loop. So I wonder, and that was one of the questions that we might discuss at the end of this session, if a different approach or a complementary approach would be trying to define sort of a benchmark data set and a set of diagnostics that each one who wants to generate a product and wants to show that this product is good should use to demonstrate the benefit of the choices that he has used. And the other thing is the comparison with the tight gauges. I mean, in our project, as Jesus showed, we decided to go with distance from the tight gauge to match satellite data and tight gauge data. The problem with that is that coastal morphology is often very complex, and therefore it can happen that points that are close in distance are actually very far away dynamically. And so maybe we should move to different type of diagnostic to try to match and decide against which satellite data, tight gauge data should be compared. And then again, is another point of discussion potentially for the end of this session. And with that, that's it for me.
Thank you, Francesca. We have time for one question, short one.
Or we can move on.
Any questions?
Last chance. We move on. Next speaker would be my co-host here in the podium, Clara Azzaro, who's gonna talk about ocean radar altimeter with the Magal constellation.
This is difficult because I cannot. Okay, hi everyone. I will present the Magal project on behalf of the project team. So in a nutshell, Magal project aims at studying the effectiveness of a small satellite constellation carrying radar altimeters. So we started by defining the use cases with which dictated the constellation, the satellite and the payload requirements and characteristics. I will also refer the Data Analysis Center, which will be responsible for data processing, display, and provision, and some preliminary results, and I will end up with some recommendations. So Magal project has been funded by the Portuguese Foundation for Science and Technology in the scope of the University of Texas at Houston, Portugal program. It meets the national ocean strategy goals and priority intervention areas. It also meets a need that has been already identified by the International Satellite Altimetry team, which is the exploitation of innovative technological concepts such constellations of small satellites carrying radar altimeters. And it is a consortium of 8 promoters. Among them, we have private companies, research laboratories, universities, and so on, and 3 partners. And we have between them, among them, the University of Texas, Austin. The project started in July 2020, and it will end by June this year. So the main project objectives are the development of a cost-effective small satellite platform to reduce launch and operational costs, and also the development of a custom radar altimeter solution with lower power consumption due to the size of the satellite, while assuring data quality and reliability. Other objectives are, of course, scientific, engineering, technological, and also entrepreneurial development. So Magal is a conceptual proof of concept, if I can say so, and that aims to provide an answer to this question, if whether or not these small satellites carrying radar altimeters can contribute to the future of satellite altimetry, and to our knowledge, this concept has not been implemented yet. So as a scientific project, Magal is divided into several activities. So in the first one, we have decided use cases, which dictated the mission definition. Then we proceeded, or we stepped into the definition of the constellation, the payload development, the satellite platform design, and during the project duration, we have been developing the data and analysis center. I'm afraid that the demonstration of the payload operation will be postponed for a follow-on or follow-up project if it is possible. So in this project, we will focus on the altimeter payload development, including the radar altimeter antenna, the information and analysis center, the constellation and satellite platform definition. So in terms of timeline and status, we have already frozen the mission requirements. So we have identified the mission, platform, and payload specifications in order to achieve the use cases, which in turn will allow us to assess the products or the measurements acquired by the mission. We have also defined high-level mission requirements and derived the system and subsystem requirements. Then we have stepped into the conceptual design. We have decided about the size of the satellite and its design, mass, power, communication budget. We have also analyzed what options we had for the radar altimeter antenna, which is the most challenging issue to solve for such a small satellite. We have also already assessed the preliminary systems interface, and we are now dealing, with this detailed design. We are also trying to decide the final equipment selection, final mass, power, communication budgets, and specifications, and that's it. So the critical design review will probably be also postponed for a follow-up project. So in terms of use cases, we have selected 4. Of course, the improve of the knowledge of the sea surface topography for local, regional, and global applications, and also the study of the water level over continental water bodies. And since we have the University of Azores as a partner, and they want to study, well, mesoscale activity in the Azores region, and also to understand how they receive such large amounts of marine debris, which is not generated there. They want to have a better knowledge about the ocean circulation, and so these use cases, this is not correctly formatted. These use cases require to improve the current temporal sampling from 10 to 5 days, while keeping the spatial sampling. So our idea is try to interleave MAGAL ground tracks with those of the operational satellite altimetry missions, such as Sentinel-3, to improve the spatial sampling with this data merging, while maintain measurements accuracy and resolution. And of course, that we know that for such a mission, we need to guarantee the precise satellite location and orbit maintenance. So in terms of constellation parameters, we have selected a sun-synchronous orbit. The satellites should fly at an altitude of 500 kilometers due to power consumption limitations. So here we have the repetition cycle versus the spatial resolution. If we want to improve the temporal sampling to 5 days while keeping the 100 kilometers spatial resolution, we need to have at least 6 satellites in orbit. So we decide to have the minimum number of satellites, of course, to decrease the cost. They will fly over the same orbital plane. Let me see if I can show you here the ground tracks of the 6 satellites. They are in the same orbital plane, and they will cover the global Earth in 5 days. So in terms of satellite platform design, the primary payload of the mission is the radar altimeter, of course. The secondary payload is a laser reflector array for ground orbit calibration. And in terms of ground segments, since under this project we will have no launch, neither we will receive any data from the satellites, we have defined the requirements, but we are not worried about this ground segment yet. So in terms of the satellite system and sensors, I believe that we have defined all of them that are needed to be sure that the satellite will fly, like propulsion systems, telemetry, telecommand communications, thermal control, and of course, the accurate attitude determination. Sorry, this is difficult, of the satellite, okay? So, except for the radar altimeter, which has been miniaturized, all the systems and sensors have been selected among what is available on the market. So they are available. So the satellite total mass will be between 50 to 60 kilograms, and the satellite shape is a CubeSat with a 24 unit size, which means that the satellite is around 40 per 20 per 30 centimeters in size. The mission lifetime is expected to be 3 years, and each satellite will cost around €500,000. The constellation cost will be, of course, €3 million, and the launch cost is expected to be around €6 million. In terms of payload developments, as I said, we had to miniaturize the altimeter, which had been previously developed by this company, which is EFASEC, and also this Telecommunications Institute of University of Aveiro. So we needed to be miniaturized in order to fit the CubeSat. It is a single frequency altimeter. It will operate for legal reasons in, well, the standard frequency. It will use this architecture based on frequency modulated continuous wave to minimize the power consumption. The accuracy of each 20 Hertz measurement is expected to be better than 20 centimeters, but after dedicated processing, which means that our colleagues will try to compute the range profile, which is the FFT of distance measurement. We expect to improve the accuracy of each 1 Hertz measurement to a few centimeters. So the radar altimeter is something like this. Well, a small box, a cube with size 1.5. So means that it's 15 by 15 by 15 centimeters size, 3 kilograms of mass, and less than 20 watts power consumption, which is also a challenge. And we are looking for a deployable dish antenna. So in terms of this, well, after frozen the radar altimeter specifications, we came up with this value for the diameter of the antenna, 1.5 meters. So it's, as you can imagine, quite difficult to have such a large antenna. It's an umbrella type of antenna deployable. Its size is too large for a small satellite. We are now discussing several options for the location of this antenna. We are trying to move on with this concept, which is the centered umbrella antenna. All of the options have pros and cons, so this one, which it seems to be the most adequate one, will not allow the installation of complementary payloads that need to have a radial direction, like for instance a microwave radiometer, due to no line of sight. The problem is that we don't have on the market this deployable dish antenna, at least for this frequency. We have antennas like this one for KA bands, but not for KU. So we have contacted several companies and there are no antenna available. However, it seems that two, at least Portuguese companies, are willing to try to develop and implement this antenna, provided that we give them all the specifications. This will be, of course, not within this project, but in the follow-up project. Well, I will not spend too much time in the link budget. I will just say that Magal will try to downlink housekeeping and science data at 20 Hz and downlink the range profile due to the large amount of data only at 1 Hz. Okay, concerning the orbit and pointing, the requirement is that nadir pointing should be better than 1 degree. And the star tracker, that is one of the sensors on board, will probably or is expected to give us enough nadir measurement of accuracy better than 100 of degree. So the ground tracks repetition is required to be below 1 kilometer. And Magal foresees it's the orbiting, which is important, currently important at the end of its lifetime, without the need of any specific maneuvers in around 5 to 7 years. So of course that we will not be able to launch the constellation within this project, but we have made some studies. The problem is that it's quite difficult, expensive to launch this constellation. So at least we are already looking for options and evaluating the launcher performance and the cost analysis, because as you can see here, the launch cost depends a lot on what type of vehicle is used for the launching. So the data center, as I said, it's just a web platform that stores the data and processes the data and makes it available to users. So I believe that in the scope of the project, all data will be freely available for the science community. It's just a typical software web development with a backend, an ETL, and a front end or dashboard development. And we expect to have multiple layers of data that users can combine and correlate themselves. So in terms of data products and latency, in using only Magal data, we expect to generate the standard products. So the data center will apply the instrument corrections to generate level 1 products. Then University of Porto will be responsible for the computation of the range and geophysical corrections to deliver the level 2 data. And then the data center will apply all the algorithms that are necessary to generate gridded products, for instance, level 3 products, or even high-level products. So, however, in the scope of Magal, since we don't have data, we will rely on simulated orbit and measurements data, and they will be provided in the data center. For grid services, of course, since we don't have complete cycles, complete simulated data for several cycles, we are not able to interpolate this data to create grids. Okay, in terms of preliminary results, and just to hurry up, So the radar altimeter, after being miniaturized, has been successfully tested at ground at the moment. So the preliminary results are fully aligned with the simulated results. We are now at the final stage of integrate all the equipment, sensors, and systems in the satellite, and the consolidation of the equipment against interfaces, which is quite important to reduce noise and so on, is ongoing. And the field tests in altitude are under preparation. Of course, that we need to look for options using a drone, small aircraft, balloon, etc., to have measurements over oceans, for instance. But of course, that we will not be able to have measurements at 500 kilometers altitude. So here we have the target in the middle of the figure and the range profile, which allow us to identify echoes from objects that are of no interest, while keep the focus on the peak for the target. So we have already performed some tests on the roof of the IT Aveiro facilities, and also some field tests in a controlled environment using simulation results and analyzing the measurements that have been made. And we can see that the results are are well aligned. So we expect, we have for single measurement an average error of that is below the requirement, which was 20 centimeters. So about the outlook and recommendations. Well, what I can say, as a constellation of 6 satellites, Magal is expected to increase the density of data. So we expect that this data can be merged with the data from the operational satellite altimetry missions. So providing more data and therefore increasing the resolution of the readed products, for instance, over coastal areas, and of course over regions of large mesoscale activity. Magal constellation should be considered an augmentation complement for the baseline altimetry missions. It's just a conceptual design. And to finish, I just want to make clear that satisfying power and size requirements are quite demanding. So these requirements are the main engineering and design challenges in the case of such a small satellite, and the main limitation is the development of the radar altimeter antenna. So we need a follow-up project to prove the concept. And so now I'm begging for some opportunities to launch a single satellite to demonstrate the performance of the radar altimeter, at least. So in that case, we would need 2 to 3 years to develop the flying radar altimeter, its antenna, manufacture and test the full satellite before putting it into orbit. And we are also looking for financial support for production and launch costs. Sorry and thank you. Sorry for, okay, thank you very much.
All right, before the coffee break, we have time for one question. I'm cool. Yeah, always.
One question then. It would be very excited to see this work, of course, because that opens up a whole possibility for small satellites, but particularly in observations at the coast where you need densification of the tracks. I saw in your plot that you had the satellites very shortly apart, just 4 minutes apart, I assume, to get the 100-kilometer separation. Have you considered moving them further apart so that you would not cover a swath that would be, all the satellites basically at the same time, 100 kilometers apart, but instead over the 5 days that you want to observe, 5 days that you want to observe, stagger them a little bit. That first in the first day you get a broader resolution, then the second day it densifies. We had the same problem with Sentinel-3, which does it also a bit awkwardly. So now you get this swath of all of them, one after the other. If you move them further along the orbit, you would kind of put them like 200 kilometers, 300 kilometers apart, and then at the next day it fills in those gaps. I think that would be a better sampling strategy than this. Yeah, of course it takes more time that they need to be separated. They need to drift.
Sorry. Oh, sorry. I will suggest this to the colleagues that are.
Yeah, sorry, just to jump in. Those as old as me will remember Tom Allen and the Gamba concept, which is very similar to this. So yeah, it's quite exciting. But just to really echo what Remco did, for doing the mission requirements, we kind of did a series of exercises looking at ocean features and sampling of them with different orbit separations.
Okay.
So I think it's an exercise worth doing to find the optimum.
Okay.
I think having a wider densify was a better.
Yeah, then you get faster repeat times at the same time. But good luck. I really hope that you can make it work.
Thank you.
Coming from Calvala, I was having a different thought on the possibility of the geometry of the orbits. I was wondering if rather than having 6 on the same path, doing like a train of 3 and a train of 3 intersecting each other. That way we will increase the number of crossovers. It will be easier to cross-calibrate the satellite one to each other. That would be my suggestion.
Yes, we thought and discussed several.
Okay, yeah, I see the point, Remco.
You need the same launch.
Yes.
So you cannot do what you're wanting to do.
We discussed a lot of options, but the launch cost is one of the most important issues that we should consider, because it's quite expensive unless we have an opportunity vehicle like we have in the ocean. Thank you.
Thank you. All right, so it's time for a coffee break. Next session, Nicolas Picot is not here, so we're gonna go directly with Doug Lichman presentation. So I would say we meet back at 6:15, and then we